Good afternoon. So today we will discuss X-ray diffraction, mainly its principle, instrumentation, and data analysis. In last class, we have discussed interaction of radiation, that is X-ray, this neutron and electron with matter, and we discussed different types of techniques that utilizes these three interactions. So one by one, today class will discuss mainly on X-ray diffraction analysis. Okay. So if you see diffraction, it is a process in which a beam of light or any other system of wave that spread out as a result of passing through a narrow surface. You can see here, if you have a narrow surface here, once that beam of light or wave, once it passes through this small orifice, so it will create a typically accompanied by interference. It will mainly produce a wave front. You see, if you have a small narrow head, here the wave fronts will be generated like this. So this wave fronts, if you see that Young's double slit experiment or the experiment, you can see here you have a small orifice here. So light is coming out here. So accordingly, you will see a strong bright spot here in this system. So that the bright spot that is the small orifice that from which the light is passing through. So then once the light is passing through this, so you will have a this interference between the waves. Then you will finally produce a wave front. So similarly in Young's double slit, you can see that this is the first light is coming here. Then it's passing through the another two orifice. You can see how these wave fronts are generated. Different wave fronts are generated. So the wave fronts are constructive or destructive interference that based on the d sine theta equation with respect to m lambda. So this is a common Young's double slit experiment where wave fronts are generated, and these wave fronts are from these wave fronts we will come to the diffraction. So if you see that this is any matter or any particle on which or any system on which that light beam or X-rays are falling on it. So after falling on this X-ray beam, they can interact with these single particles and then it can scatter back in different direction. So it can be scattered back. So this X-ray light is scattering uniformly in all directions. But if you see in case of diffraction, a diffracted beam mainly defined as a beam composed of large number of scattered rays, but they are mutually reinforcing each other. That means you have a plane here. You can see these yellow lines are planes. Once this X-ray beam or light are falling on this, so it will interact with that on solid or the crystal, and it is diffracted in particular direction. You can see one is diffracting like this. So like that, if one is diffracting like this, the another, if it's diffracting like this, then this is a constructive interference. You can see all the tufts and are on the same point. So depending upon that, you will see there is a constructive interference, or if it is like one is like this, another is going like this, then it may be a destructive interference. So all diffractions are scatterings, but all scatterings are not diffraction. So the diffraction occurs only when they are mutually reinforced with each other with a particular relation, that Bragg's law. So that we will discuss it later. So if you see the interference and diffraction, you can see this is the red line is one wave and the black is another wave. So you can see here they are constructive interference. That means the scattered wave beams interfere constructively in some direction, producing so your overall intensity will increase because of this two waves. They are constructive interference, where phase difference is 0 degree. If phase difference is 180 degree, if you see here, you can see the red line and the blue wave. So you can see they are cancel out each other. So that means it's a completely destructive interference. When theta is not equal to 0, so in that case you will find, but not 180, in between that you will find that there is random arrangements. So cause some randomly interference and no distinctive pattern we will see in this case. Here you can see the blue, black and red lines. So they are, though they are a little bit constructive, but you will not see a distinct pattern here. So diffraction occur when light is captured by a periodic array with long range ordering, like that you have a crystal or you have a polycrystalline material or any crystalline material in which, or a single crystal in which that atoms they are arranged in a periodically, like these atoms in the lattice if you see, so these atoms will be arranged periodically. So they are ordered atoms on this is one plane, this is another plane. So if the atoms are arranged properly, then only periodic array, then for a long range you will see a constructive interference. So then only the diffraction will come. So before going into the details of the full study of X-ray diffraction pattern, we'll see a little bit about history and background. So in 1895, X-ray was first discovered by Rontgen, and the first diffraction pattern of the crystal made by Nipping and von Lau. So they have 1940 the first diffraction pattern they record. The theory to determine the crystal structure that by the Bragg's it's come around 1915, and then it was keep on developing the different types of X-ray techniques and powder X-ray come into picture. So finally in 1947 the first commercial diffractometer that Philips PW 1050 X-ray the machine was discovered, and using this technique in 1953 that scientists that Watson Crick they solved the DNA structure. If you can see here, this Rontgen, this is the X-ray of the hand palm. You can see there is a ring here. This X-ray was the photograph of Rontgen's wife's hand's X-ray that Rontgen has taken, and because that time he doesn't know what is this so he named it as an X-ray. X-ray, that means unknown compound he named it. So X-ray diffraction is similar to that of the multiple slit experiment. That means first one, or if you second, third, like that. If you see a multiple slit experiments, it's similar to that. And constructive or dexterous interference patterns that mostly depend upon the lattice spacing, how the crystals are arranged in a plane. If your lattice planes are like this, on the arrangement of the lattice plane, as well as the wavelength of the radiation. And the wavelength of the X-ray is similar to that, the distance between the atoms. If you see the diffraction planes, they are about angstrom levels difference. So for example, copper K alpha is 1.54 angstrom, molybdenum is 0.7 angstroms. So these 1.5 points per angstrom, there are interplanar distances. So we are using a wavelength that is almost equivalent to that of a lattice plane, and to find out that crystal structure and all this. So this we have already discussed in last class, how the X-rays are produced. In X-ray, we have a X-ray tube. Inside that tube, we have a cathode and an anode. That is the target here. This is the target anode. And this cathode, we have a thermonic emission of, because there is mainly tungsten filament. From there, the thermonic emission, high-speed electrons are coming. Those electrons are striking on this target, and then X-rays are produced. And these X-rays are taken out through high electropositivity. So once the X-rays are produced here, so you will able to see different characteristic X-ray as well as background X-ray. You can see here, this is the continuous spectrum, that background, that is mainly due to the Bremsstrahlung radiation, and on that you will see K alpha 1, K alpha 2, or K beta. These are the characteristic X-ray. As we discussed that K alpha is mainly produced from L to K transition, beta will be M to K transition, and similarly gamma is from N to K transition. And from this, if you go for K alpha, K beta transition, so that K beta can be separated by using nickel filter. That for copper case, that Z-1 formula, and K alpha 2, so they can be even distinguished through synchrotron XRD. So this we have already discussed. So if you see here that different target metal molybdenum, its wavelength is about 0.7 angstrom. In case of molybdenum, we have Z-1, that zirconia is the filter, and you see that the wavelength is about K alpha K is 1.54, 056 angstrom in alpha 1, and alpha 2 is 1.5439 angstrom. So if you see that K alpha 1, K alpha 2, and beta ratio, it is about 6:3:1. So this is the common thing how X-rays are even formed. And then coming into XRD, X-ray diffraction pattern, the atomic planes of a crystal structure of an incident X-ray. You can see here, this is a substrate here, that substrate is here. Then your incident beam is falling on this. So this incident beam is highly monochromatic. It should be highly monochromatic, and we have material if it is crystalline, then you're able to see those long range ordering and able to get that X-ray diffraction pattern. Otherwise, if it's amorphous, there is no long range ordering, only short range local ordering, you'll be able to see a broad spectrum. So mostly this incident beam will falling on the sample, and in diffraction at an angle that if you see the diffraction angle is 2 theta. So here this is the transmitted line to the diffraction, the angle is 2 theta. And this if non-destructive X-ray diffraction pattern is a non-destructive techniques to identify the crystalline phase and the orientation of the materials. So it mainly measures, the X-ray mainly gives D spacing, a lattice parameter that A, B, C, whether it's FCC, BCC or SCP, those things can be identified. You can identify the crystallite size, phase composition, even atomic range, arrangements, and stress or strain built up in the material, which may be due to the defects or due to the doping. So whatever the stress is generated, that you can also measure. So it also gives crystal structure of unknown material. If you have unknown material, you can identify what is that material, whether the phase, which phase is, that those things can be identified by X-ray diffraction analysis. So main that limits that X-ray detection limit is 2 to 3%. There is a two-phase mixture up to 2 to 3%. Doping can be identified. So below this, it's difficult to distinguish X-ray diffraction technique. So it can even by conventional XRD, but if you go for a synchrotron radiation, so there it can be resolved up to 0.1%. So mainly within the limit, you will able to get the crystalline plane, so that you will see whether the phase is formed. And especially that X-ray beam that we are using, that should be coherent, monochromatic, and it should be parallel with the wavelength of lambda. If you see here, this whole diffraction pattern which diffraction will occur or not, that will depend upon the very well-known Bragg's law. So the Bragg's law satisfied means you will see the diffraction pattern. So the Bragg's law is n lambda equal to 2d sine theta. So n is the order of reflection, per d is the d spacing between the planes. You can see here, so that these red lines are plane. You can see this is plane 1 or 2, and then the two beams, X-ray beams are falling. You see the beam 1 is coming on the one plane, it's getting back, and similarly beam 2 will come here and it will go diffracted. So if you see here that if you draw a perpendicular from here to here, and this angle with theta, so this is the extra path length that from here to here and here to here, the distance is same. And again from this to this, the distance is traveling same. So and this. So this is nothing but d sine theta. So d sine theta plus d sine theta, that is, is 2d sine theta, and that should be equivalent to the integral multiple of wavelength lambda. So the 2d sine theta is equal to n lambda, then only your Bragg's law satisfied and able to get a proper diffraction pattern. So if you see the Bragg's law, that n lambda equal to 2d sine theta, you can rewrite this as sine theta. You will take the other side, sine theta equal to lambda by 2, this lambda by 2 by d HKL. That is nothing but this lambda by 2 by d, that is equal to 1 by d lambda by 2 by lambda. So if you rewrite this equation and then you draw a circle with the diameter, this 2 by lambda is the diameter, this diameter will be the 2 by lambda. 2 by lambda is the diameter, and construct a triangle that here, this is a triangle at a point from P here, where that one side is 1 by d, that diameter is a hypotenuse. If you do the diameter as a hypotenuse and 1 by d scale is a side, and you will get a triangle that this angle is always 90 degree, that AOP. And then what will happen, the theta opposite to this PQ line, you will have a theta. You can see here the sample is kept here, and incident beam is falling here and is diffracted in this direction. So that means this will be a 1 by d, that 1 by d you can express a d star, that will nothing but in reciprocal lattice. So d star equal to 1 by d HKL. So this whole sphere is called UL sphere, and this UL sphere, whatever the point that lies on this circle, this big circle, so that planes you will be able to see. You can see here that this is the sample here. On that sample, you have X-ray diffraction pattern is falling, and then you will be able to see that particular this point, for example, point B, and this point B is here, and then that 101 plane lies on this circle. That means you will be able to see that points. So diffraction maxima, either is reflection, you can say, or diffraction spot, occurs only when Bragg's equation is satisfied, and this condition occurs whenever a reciprocal lattice point lies exactly on the UL sphere. If this is the UL sphere, on that surface, if a point lies here or here, if that point lies on that circle, you will be able to see a Bragg's law satisfied, and you will be able to see that particular diffraction patterns. So if you see the order of reflection, that n lambda equal to 2, the 2d sine theta, the equation that we use, n lambda equal to 2d sine theta, this n is the order of the plane. But you can see here, if you have for d 100, that is equal to a by root 2, for d 220, a by root 8. So that means sine theta and theta, you will call faster reflection plane 100, and second reflection plane 100 of that, and faster reflection 220. Though if you keep on increasing, you will see d220 by d110 equal to 1 by 2. That means in a cubic relationship, you have a d cubic. So for a first order plane, it's equal to a by s square plus k square plus l square square root. If it's nth order plane, nh and k and l is a by nh square and k square and l square. So that means if you d nh and k l y equal to a, and you can take out of this n square root square in all case, so a square plus k square plus l square. So this is nothing but your DHKL. So that means DHKL divided by N. So from that nth order reflection of HKL plane, that means if your nth order plane is equivalent to that of HKL plane, treated as a first order plane of the spacing D by N. So that means if you take 111 plane, 222 plane, or 333 plane, if you take like this type of plane, so that means that first order plane of this will be NHK, that this plane will be order of t stage d by n. So this is the common relation, and we know that Bragg's law is a negative statement. That means if Bragg's equation is not satisfied, there will be no reflection. No reflection will occur. That means you will not see any diffraction pattern. But if Bragg's law satisfied, a reflection may occur. That doesn't mean that if Bragg's law satisfied, a reflection is always occur. So, but in the other way, it may occur. So thus, even though a Bragg's equation satisfied, the reflection may not occur. So therefore, it's a negative statement. For example, if you will see, you can see I have shown here is a molybdenum BCC crystal, MO BCC crystal. You can see this is top plane, this is bottom plane, and in between these two green plane, there is a red orange plane here. And you can see here the light, that the X-ray diffracting from this plane with the wave scattered from the middle plane is out of phase from the top and bottom plane. So that means here, instead of this n lambda phase difference lambda here you can see this out of phase. So this is not, instead of lambda, it's lambda by 2. That means this particular plane we are not able to see that X-ray diffraction pattern, because the wave scattered from the middle plane is out of phase, and because of that we will not able to see. But the first order reflection from the 200, like this is the first order plane, is a 100 plane we will not able to see. But if you go to the higher order plane, so you may able to see, because their path difference is lambda. So this we can identify that how that Bragg's law is a negative statement, and some peaks are missing. You can give an example here. We will discuss. So that one NaCl and KCl, if you see that they both are in FCC type structure here. So in that case, if you see the sodium and chlorine atoms, they are arranged like here. in a proper fashion, you will see all sodium and chlorine atom adjacent to each other. And the closed pack layer of the structure is thought to be composed of two interlinking CPP structure with Na plus and Cl minus ions. The closed pack layer of chlorine lies parallel to the body diagonal and halfway between one and one. And if you see that chlorine, the chlorine and this sodium here, so you can see that they and the KCl in case of potassium and chlorine, so they are both have 18 electron. Since that Cl minus it has 18 electron, and that one electron will taken by with Na plus sodium Na plus that is having 10 electron. But if you see the KCl, K is again 18 electron and chlorine is 18 electron. Here it is 18 electron, but here it is 9 electron. So here is these two K and Cl, they are isoelectronic. So because of this isoelectronic, what happened that that the X-ray beam diffracting from the K plane and Cl plane, they may be reinforced with each other in such a destructive way, so that what will happen, you will not able to see all planes because of these isoelectronic things. If you see here, you can see this is a 1-1 plane here, and here you can see here. So in case of NaCl, because of they are not isoelectronic, so you can able to see this 1-1 peak here. But if you go to the KCl, in KCl, the reflection from 1-1 layer containing K ions is exactly out of phase with that of the Cl minus closed pack structure. So being isoelectronic, so reflection or diffraction intensity from K plus and Cl minus, they will be identical. So the net effect is that the two reflections cancel each other, and you will not able to see the 1-1. You can see here almost it is gap is vanished. So this is the example of how that some missing planes that we discussed, and this whatever the planes you will able to see, that depends on the selection rule or the extinction rule. So we have seen that even Bragg's equation is satisfied, the reflection may go missing. So this is due to the presence of additional atoms in the unit cell. Like if in case of BCC of a center atom, we discuss molybdenum, but in case of KCl and HCl, we discuss with how they are isoelectronic. If you see that simple cubic, the reflection, all reflections are possible is present, but body center, when HK plus L, H plus K plus L, even you will able to see a reflection, but if it is odd, you will not able to see the reflection, in this case diffraction pattern. But in FCC, if it is H, K, L, unmixed, take all order, all even, then only you will able to see a plane. So you can see, just this derive this equation, that ratio of S square plus K square plus L square derived in the extension copy rule. So that will determine which lattice type of plane. You will see in case of simple cubic, it's 1, 2, 3, 4, 5, serially you'll be able to see, but BCC 1, 2, 5 up to 7, here is 7 we see. But in FCC is 3, 4, 8, 11, 12. So this type of H square plus K square plus L square value, that will be possible in this case. You see, if you write that all allowed reflection like this, like you can see this 7 and 15. So here you can't express this as H square plus K square plus L square. That means this plane will be completely missing in all either SC, FCC, BCC, or diamond cubic structures, you can see. So like in all other cases, you will see some specific planes here. So this diffraction, what we discussed so far, so the diffraction pattern can be taken by 3 different methods. Main one is Lau method, one is rotating crystal method, or powder X-ray diffraction method. If you go for the Lau method, where wavelength is variable, but angle is fixed. So it's mainly used for a single crystal, similar rotating crystal, that they are also wavelength fixed, but angle is varied. That is also used in a single crystal. But in case of powder, that will happen, that is the wavelength is variable, it is fixed, that was angle is variable here. So this is the powder spectrum. So this is either single crystal or powder, that depending upon the material you can choose which one you have to do to get the proper crystal structure. In case of Lau method, that single crystal uses single crystals, and it's used for determining the crystal orientation as well as quality of the materials. A rotating crystal method determines of unknown crystal structure. If you don't know the crystal structure, so those crystal structure can be found by this rotating crystal structure system. But third one, if you see the powder diffraction method is most widely used, is determining the crystal parameters with high precision and identification of such. So where your wavelength is fixed, for example, in case of copper, this copper K alpha, that's 1.5405 angstrom, but the angle is varied. And this angle, if you see, so that can be varied in two different ways. So that will come little later. So out of this, today we will mainly focus on the powder diffraction method. If you see, this is cone experiment, that X-rays. If you see here, this is the sample here, and then from the sample you have a photographic film here outside here. The X-rays are scattered from the sample in a sphere that's around the sample, and a cone along the sphere corresponds to the Bragg's law. If an angle is here, if you see sample, whatever the diffraction beam you're varying the theta, you'll be able to get like this. So you'll be able to get, and you will see, perfect a conical structure like this. So all the diffracted beam that form a cone along the spheres, the terms of the thousands of randomly oriented, the tens of thousands, like if you have polycrystalline material, it has 10,000 randomly oriented crystals, so that they produce this cone. So that means you will get a multiple cones, a divide-Serre cone or divide diffraction cone. So particular plane or diffracting this direction, that is forming one cone. Another cone you see is forming here. So like this, you will be able to see cone in this direction, as well as you can also see cone in backward direction also. For a small fraction of crystallites, the sample actually contribute to the, out of that, if you take a large quantity, only very few samples that will, small fraction of crystallites in the sample actually contribute, because whoever is aligned with the, that X-ray beam where the diffraction is for those will contribute to the diffraction pattern. So number of crystallite side that contributes to be measured a pattern can be increased by spinning the sample. Like in a single crystal system, if the sample is falling on the X-ray, so if this sample is under spinning, so what will happen? Your interaction will be more, so more crystalline plane can be come into picture. So amount of scattered X-ray observed can be increased using a, if you have different types of detectors are used, whether 2D, 3D detectors are used. So we based on those detectors. If you have 2D planar detector, so what will happen? You can able to increase the scattered X-rays. So if you see here, the sample crystal plane is here, and the crystal is kept here, and the crystal plane is somewhere like this, aligning, and incoming X-ray is falling on this here, and after falling is getting diffracted. So then you will be able to a UL sphere. On the UL sphere, whatever the point phi that lies on this particular, this UL sphere, so you'll be able to see a powder diffraction pattern. And after that, this film, if you see here, so this film, we have a small hole here, and you have a small orifice at the end also. So once this beam is passing through this, so you'll be able to on the two spot here, first and second spot, so all orifice, and then you'll be able to see this type of planar arrangement, because whatever the cone is falling on the film, you will be able to see this type of plane. You can see here the arc, that S1 arc here and S2 arc here, that arc is, this is S1 arc and this is S2, that big arc. So 2 theta is the angle here. So whatever the theta from front reflection, whatever the front side reflection, that is pi S1 by 2W, per back side is pi by 2 minus into 1 minus that S2 by W, the back reflection. That means for Bragg's law, you will able to satisfy here. Then for a cubic crystal, d cubic equal to 1 by S square plus K square plus L square. So this S square plus K square will be 4 S square by lambda square sin square theta. That means your H square, K square, L square is always proportional to sin square theta in case of this type of spectrum. So once you have taken a XRD pattern, you have to identify which type of phase is found, whether it is an FCC structure, crystal structure, BCC or SCP. Those can be indexed properly by using a simple sin square theta law rule here. You can see, so whatever the theta position is here, because this S1, S2 arc in conventional currently available XRD, which directly gives this theta value. Earlier we use board, this big graph paper type where you used to stress our X-ray, and there that we used to measure that the arc value, and then from the arc value we'll be able to get theta using the previous equation. Since we know the theta and we will able to get that sin square theta value. Once you have this sin square theta, so what you do, that sin square theta divided by sin square theta minimum, you can see sin square from 0.11 to 0.99 is there, so you divide the lowest value, this 0.11, you will get sin square theta by sin square theta minimum, like this will be 1, and accordingly it will increase. So once you find this sin square theta by sin square theta minimum, what you do, you make it a whole number integer. So that whole number integer, you can see that if you multiply 3 here and 3 all those things, so they are coming almost, it's 9 into 3 27, 24 into 19.9, so you can take it as a 20, then since it's 19.084, you can take 19. So once this value, what you get, that 3 into this, so that will be your whole nearest integer will be S square plus K square plus L square value. So then based on this, if the S square plus K square is equal to 3, so that means H should be 1 plus 1 plus 1. The 1 square plus 1 square plus 1 square, that will be 3. So it means a 1 1 1 plane. Similarly for 4, it will be a 2 0 0 plane. For 8, it's a 2 2 0 plane. So like this, whatever that whole number you are getting, so those whole number you convert to that HKL value, and what you will see in all this case, if you use the a lattice parameter equation here, you can see A, you want to a cubic system, so A equal to B equal to C in this case. So in that case, A equal to S square plus K square 4 A square by lambda square sin theta. Using this formula, and what will happen, you will able to get the lattice parameter. Then see, the lattice parameter is constant, that is A is constant here. As you know, for FCC structure, A equal to B equal to C, and alpha equal to beta equal to gamma equal to 90 degree. So that means that since A, B, C, all three are equal here, so this crystal structure, whatever we formed, this diffraction pattern, so that is a FCC structure. Okay. So then if it's a hexagonal or trigonal structure, tetragonal structure, orthonomic structure, you can use different type of formulas to find out, whether the proper crystal structure. So for hexagonal closed packed structure, you can see, you can write a S square plus K square terminology separate, and C by A terminology separate way. So that HKL, that L equal to 0 is one possible in this case, and L square by this C by A whole square, that is 0 0 L plane, you'll be able to see. So that means you can identify the crystal structure, whether FCC or not, or SCP, by using crystal structure indexing. Okay. So far what we discussed about the theoretical background towards the X-ray diffraction pattern, and little bit about how to analyze the spectra, whether it is FCC, BCC structure by using sin square theta by sin square theta minimum formula and making into whole integer, and then to identify that particular HKL plane. So for a powder X-ray diffraction pattern, if you see, this is a common picture of that. You can see here, you have an X-ray tube here. Right now, here in left side X-ray tube, and from the X-ray tube, the X-ray is going to the sample is the sample substrate on which is the sample on the white surface, sample cells here. And once that X-ray beams are coming inside and falling here, so after that, from the diffracted beam will go to the detector by using different slits as well as monochromator. So that X-ray will go to here. So there will be detector. So that detector will identify the diffraction pattern. So if you see the major component here, you have a source, X-ray source here, this one, and then you have a sample stage where sample is kept, and then you have a filter. Different types of filters are available, and then variable slits. These are the sub slits, then the mirror and planes, and finally a detector is here. So that detector will be gather the information from the samples, and it will be connected to crystal structure, can identify. So if you see the powder diffraction pattern, so there are two types of powder diffraction pattern. In one type of instrument is theta to theta experiment, that is source is fixed and the sample rotate theta minimum to the detector, and the detector rotates at 2 theta minimum. That means in this case theta to theta, your source, that X-ray tube will be, that is fixed, and you can able to sample can be rotated at 0 degree per minute, and the detector rotates 20 degree per minute. That's possible. So whole thing, the focusing plane here, you can see on the plane so the X-ray and detector both lies on the focusing source. In a theta instrument, on the other way, the sample is fixed and the source rotates at the rate of 0 degree per minute, and detector rotates at the rate of theta per minute. That means in this case, the sample is fixed. Here in earlier case, theta to theta, your source is fixed and other things are variable, but here sample is fixed and source is fixed. The source is, sample is fixed and source which rotates this angle. So if you see the powder diffraction diffractometer typically uses this geometry where X-ray tube and focusing that sample as a detector, they lies in a circle that is nothing but called Bragg-Bentenov geometry. Here the diffraction vector S, you can see here, that is the normal to this surface and bisects the angle between the incident and scattered beam. And user can choose to move the sample and the detectors, fixed source or detector source, sample stays fixed at the center. So you can either way you can choose, and you can to get the XRD patterns. So if you see, once the XRD pattern is formed and after falling on the sample, that X-ray goes to the detector, and in the detector we used to identify, or the detector used to give a spectral to that X-ray diffraction pattern that we used to identify. You see, different type of detectors are used. Like the detectors can be point detectors, line detectors, or area detectors. If it's a point detector, your GM counter is there, professional counter is there, scintillation detectors are there, silicon lithium semiconductors are there. Then like in line case, you have a 2D VSD or fetch array is there, but in case of 2D detectors with all photons scattered in conical detectors, like there you can use a CCD plate or a image plate or a photographic film. What will happen? It will give more better information about the sample. You can see here, you have an X-ray tube. Inside the X-ray tube, you have a cathode and anode, and that will be filled by krypton, argon, or xenon with quenching gas such as chlorine, bromine, alcohol inside that. And then when X-ray beam is falling on this, what will happen? You will see some constructive interference, and because of that, your detector will get the signals here using professional counter. So it counts all photons within the energy window that hit them. You can see here, this is the ionization chamber, then professional chamber, this is the gigamolar glow you will able to see. So that will help you, high counting rate is possible in case of GM counter, and good resolution you can obtain. In another way, if you see the scintillator detector, in scintillator detector, you have a sodium iodide thallium film here. When the X-ray fall on this, it produces, some sort of, light or electrons will be produced, and that electrons will be passes through the different diodes are there. You can see these are the diodes, and each time this capability of, multiplying that, you will get a photomultiplier tube that will use sodium iodide thallium and cesium Sb metal. What will happen when the light, these X-rays fall on this, the sodium iodide, then some light signal will be produced, and then will be amplified by this way. The amplification factor is very, very high, that is 10 to the power 7 order. Yeah. So in this diffraction pattern, the diffraction pattern depends upon the material properties, whether it's material is amorphous or crystalline. Depending upon that, you will be able to see the crystal structure patterns. So if it's a completely crystalline material, you will see sharp peak like this type of sharp peak you will be able to see. But it's a diffuse peak that you are getting a broad peak here, so or a amorphous peak that you are getting. That means the structure is not completely formed and you are able to get some amorphous material. And even if no water, no fig is observed in case of monoatomic gas, or in case of this is liquid. So identification can be possible only when you know what type of material it is formed, whether it's amorphous or soft crystalline material. That then you go and compare with the currently available literature, ICCD database or JCPDS database to identify your peak. And that the two ways diffraction pattern can be measured. If a solid sample, X-ray can be incident and it can be diffracted. But here in case of liquid sample, you can also see that the parallel beam is falling on the sample and is getting scattered. That is for liquid sample. Especially liquid and monoatomic gas, you will be able to see this type of graphs. Okay, so this atoms, in case of if you liquid sample also, instead of this, like you can also do, if it's a cuvette with sample, and you can also inverted X-ray type, you can able to do also where it's after interacting, it's from the bottom part, it's coming out. So that can be done in case of liquid samples. So if you see, there are mainly two types of crystal structures have come across. One is single crystal and polycrystalline material. So in polycrystalline material, you have many, many crystals are arranged in that. But for a single crystal, there is only one orientation in real space, resulting one orientation in reciprocal space. If you see in the real space, you will see that these dots are there, so they are periodically arranged here, and the corresponding reciprocal lattice, you will see this type of dot planes. But in case of but in rotating crystal, that will be rotating the crystal rotates the reciprocal lattice. Like in this case, it is aligned in this direction. If you align in this direction, slightly rotate the crystals, what will happen? Your diaphragm, your reciprocal lattice, so that is when you see it can each has been tilted. So mostly in single crystal, there is only one orientation that will be aligned in a particular direction. You can see here with the single crystal, all the planes are aligned in one direction, and the X-ray beams are falling for whichever Bragg's law satisfies. They are diffracting them from this plane. So you can see you will be able to get this type of spot in case of single crystal. So sharp spots you will be able to see in case of single crystal. But if you see that X-ray diffraction pattern, you can see in the whole X-ray diffraction pattern here that is shown, you can see only that 100 peak is there and 200 peak is there, whereas at peak at 1110, 1 here 1110, 111 and 210, there is no peaks. That means 100 peak here you can see, so they are aligned in a particular direction, so that they are in periodic array, so electron lie, these X-ray beams are properly diffracting. But if you go to 100 plane here, so you can see that's a tilted here. So that means in this case, it doesn't satisfy the Bragg's equation, or in this case. So instead of that, you can see here this 200 plane. So that is again matches with the 100 plane, that is second order plane of that. That's why you are able to see the 200. Similarly, you can able to show 400 peak and so on, because that is because of the periodic arrangement. In the single crystal, you can see a family of atoms that corresponding to these diffraction peaks. But in case of crystalline material, the powder sample consists of many crystallites with the random orientation. That means in a powder sample you take for an XRD, what will happen? You have many powder, many crystals are there in that powder samples. So what will happen? So once you can see here these three blue planes here and some other planes are there. So these three blue planes, if you see, so they are oriented with the incident beam. So there is a diffracted from this. So if you slightly rotate the sample or slightly changing the position of X-ray falling on this substrate. So what will happen? You will see another some other plane like this 1, 2, 3 plane. Instead of these 3 plane, there may be 4 or some other planes. So those plane will be now oriented with that X-ray beams. So able to see another plane. So if you see for a particular plane here, first plane, second plane, third plane. So like if this 1 dot, 2 dot, 3 dot like that, there is n number of crystals are found. So these dots are will be many dots are available there, and these all dots they fuse together to looks like a ring pattern. Ring pattern. So you can see the polycrystalline material. So different spots are observed. So they are that is there is n number of lattice crystals are there, so you'll get many diffraction spots. And you can see here we have a 100 plane, so that is parallel to that incident beam. So it's 100 peak is there, 110, 111, 200, 210. All the peaks are possible here in case of polycrystalline material. For every set of planes, there will be a small percentage of crystallites that are properly oriented. That means whatever that you are taking some chunk of sample, so on that sample for every set of plane will be a small percentage you will see the crystal is oriented. So because of that you will be able to get particular beams and particular X-ray diffraction pattern you will see. You can see here the diffraction pattern, that is a zinc plane, ujite, and a nanotetrapode. So these are, you can see here, they are all you can see how different type of crystal plane. This is a zinc plane structure, this is a ujite structure of zinc oxide or zinc sulfide nano tetrapods. You can see different peaks you are able to see. So in that way, the structure A is ujite structure and B zinc blende structure. Here see how the atoms are hexagonally arranged here and how so because of best ujite structure is a zinc blende structure, you can identify which phase of of your material is formed by the diffraction techniques. In case of nano tetrapod, you can see it's a nano size. You can see a broad peaks you are able to see here because of the nanocrystalline feature. So the crystal structure describes the atomic arrangement of a material, and when the atoms are arranged in differently, so you will be able to see different diffraction patterns. You can see the atoms arrangement here, and here this atom is tetrahedrally coordinated here, and how the atoms are arranged here, because based on the atomic arrangement your diffraction patterns is different. So then we will see that how that you can analyze this diffraction pattern. So after we will take a short break here, 2 to 3 minutes, and then we'll discuss this how to analysis of the after. So far we studied how the diffraction patterns are formed and how to identify whether the FCC, BCC, or what type of structure is formed, and then we'll come to the analysis of this how the phase. That's a short break. So far we have discussed how the diffraction patterns are formed. So once you get this type of, highly, diffracted planes, like all different planes you observe, so how you can identify this phase? So to identify this phase, you can simply, refer to, if a known sample, then you can go to JCPDS or ICDD database, where you can identify. You can see here, once you have a diffraction pattern, for every phase is unique. That is for different types of sample, your phase is, is a unique diffraction pattern. So that is like our fingerprints. So you use this position. If you can see, this is the position, what is the angle position here. For example, it's around 31 degree. This is around 45 degree. So in the 2 theta value, that peak position, and then you have to see how the intensity. This is 100% intensity, and this is 80% intensity. This is 20 to 25% intensity. So based on this, so if you are able to see, so the two things, one is peak position and intensity. By comparing these two with reference database, you will be able to find out what phase is informed. So I have taken here a common example. You can see here 2 theta value was mentioned here, and corresponding this spacing that available that I have given here. So and current intensity is also here. So you can see here, among these, the most intense peak is here at 2.82, that 31 degree, the D spacing 2.82, that is 100% intensity peak. So if you see here this peaks, and then you can see what happened. So identify the first 3 strongest peaks. The first 3 strongest peak is your 100%, then you have a 60%, then you have a 30%. The first 3, this is first, and this is second, and this is third. The first 3 strongest peak, first you have to identify it from the database. So this database I have taken from JCPDS, or then you first strong 3 peaks. So then that sort the JCPDS manual to find out the D spacing belongs to which component, which compound. You can see here, this is the things that I get from JCPDS database. This is my the XRD pattern which I got. You can see here, I have so many, about 17 substances that have similar nearly D2, but only 4 have D1 2.82. You can see here, I found there are 17 elements which are available in the JCPDS database, but only similar D1 that you have, this 4, you can see 2.82, 2.82, 2.2, that 4 have similar, D1 spacing. So there will be ERAC2Q or NaCl or this ammonium tungsten oxychloride or this one. So out of this, only out of 17, only 4 matches with that, with the D spacing of first flame, that's 2.82, and then you see out of these only one, that is 2.2 hits matching here, and second one you can see 1.99, 1.99, that is also matching in second case in our 60% intensity. But if you see the third plane, in the third plane which you're getting 1.63, so in that is matching only with this one. So that is with NaCl crystal structure, only D3, the third plane is matching. That means your crystal structure is NaCl. So by seeing the first 3 plane, by comparing that peak position theta value as well as with that intensity, so I can able to identify which is my phase, what phase is really my material have. So you can identify if an unknown material like this way. If an unknown material, so those can be identified by using trial and error method, or you can go for a extensive Goodwill analysis or so to find out what the crystal structure is formed. So I have just given a basic example how to find out, and then in addition to that peak, that in XRD pattern, what you see, we are getting a peak like this, and the peak, that position, from the peak position in earlier slide we discussed, from this peak position we can able to identify how these particular peak positions are there. These peaks are present. That means you have a NaCl structure. So that you can identify by using this, X-ray diffraction. So once that peak from the peak position and that 2 theta peak position value as the intensity, you found that this phase is from. In addition to that, you can get many other information from the XRD pattern. If you see that, if you see a peak, so that XRD peak, if you'll see, so you'll able to get this type of profile. If you'll see peak profiling, so if this type of broad peak you wish to see. So this peak, you can see instead of sharp delta function, normally that XRD you will able to get a delta function. Instead of delta, you are getting this peak broadening you are observing, and that peak broadening is mainly due to due to that due to particle size effect, strain effect, or some instrumentation effect. So because of that, you are getting this broad. So this broad peak is summation of instrumental peak, like the unresolved alpha 1, alpha 2 peak, non-monochromaticity of the source, because source is not it's not monochromatic, or imperfect focusing is there. Your sample is lying here, and instead of focusing to the sample surface, you are focusing a little off focus here. So that means you will not able to see proper, this broadening you will able to see. Another aspect will be crystallite size in the vicinity of theta b. So there is a negative Bragg's law equation is not being satisfied. That means you have that crystallite size, that small size is there. Because of that, that in a perfect, if you take a perfect bulk metal, there are number of planes there, and then if first one plane is here, that another plane is there, that 180 by nth plane will be perfectly destructive interference the top plane you will see. So if this in nanoparticle, what will happen? So some planes will be missed there. Because of that, you will able to see that not all destructive interference will not be there. So some peak broadening will able to see because of crystallite size. And then the strain, whatever the residual strain arising due to dislocation, precipitate formed inside, inhomogeneity in structure, or solid solution limiting. In that case, you will able to see some strain effect. In addition to strain, you will able to see stacking fault. That means the atoms are used to arrange in a periodic like this, like this, like this. Instead of that, if some planes are randomly changes its orientation, instead of the perfect plane that appears from the plane here, you can see these are the stacking fault. So that you will be able to see different types of stacking fault effects that we observed. That will also give to broadening, and some other broadening can be possible. That means whatever the peak broadening you are getting here, so that peak broadening is mixture of you can see it's a mixture of this, the peak broadening that you are getting. So that is a mixture of instrumentation, then this crystallite, strain, and stacking fault. All these, instead of this delta function, that black line, you are getting all these summation of these peaks that you will able to get a peak broadening. So once you want to calculate the crystallite size, the strain, you have to do some corrections. That instrumental correction you have to do, you have to apply that instrumental correction. Before going to do your XRD, first you have to take a single crystal, like for example, you can take silicon single crystal, and you take a XRD pattern at 27 or 28 degree, you should see a highly delta peaky like this sharp line. But if because of instrumental broadening, you may, instead of this, you may ended with a slight broadening of the peak, you will able to see here. So that will be due to the strain, that the instrumentation effect. So that has to be subtracted. So most of the instrument, it follows either laryngeal profile or a Gaussian profile. If it's following a laryngeal profile, it simply it will be B minus BI. You'll able to get that BR. You'll get from the by B some standard, that is BSB or B standard from B instrumentation, that is to be subtracted in this way. But if it is a Gaussian peak, you can see that B square minus B standard square minus B sample square, or sorry, this is B is B sample minus B instrument, that has to be subtracted here. For a geometric means, in this way you can find out depending upon your instrument, what type of profiling is following, you can subtract that instrumentation line broadening. So once instrumentation line broadening is subtracted, then you will get the peak broadening due to strain and stress. In addition to that, there are some other experimental error you have to eliminate while X-ray taking X-ray diffraction pattern. You can see here, this is the sample surface, the specimen. If your X-ray tube is not properly aligned, instead of falling here, if X-ray is falling here from a little bit off position, then there will be a error due to that del 2 theta error will be there. So that peak position has to be properly fixed, and most common type of experimental error is the shift in the peak due to slight that lifting in the sample height. The sample is changed in the position. So large error generally in low theta peak, you will able to see if you have instrumentation is not properly done. You can see here, if you plot this d by d, the variation change in d by this, you will be able to d minus d theta by tan theta, and you plot that 1 by tan theta is nothing but cot theta versus 2 theta. You can see here this low intensity peak, that low angle, you will be able to see the large error in this case. So instrumentation misalignment, those things has to be taken care. Once those things taken care, peak broadening due to instrumentation is separated, then you will able to find out the crystallite size by using Scherrer formula. So that that peak broadening from the peak broadening, so this will be your this height will be this is full width half maxima here, that this FW beta, this one, that FWHM or B you see here, full half width, full width at half maxima FW, this is FW HM. You will able to see from there. You can calculate that K lambda by L or beta cos theta. So L is nothing but this beta that cos theta, you will able to find out. So here the Scherrer formula has a many drawbacks, like it consider the sample is highly spherical first things, and then it is valid up to certain size that beyond 100 nanometer. This Scherrer formula doesn't work properly. So this L equal to consider 0.8 lambda, 0.89 for a perfectly spherical systems. This is 0.89 lambda by L cos theta. So for strain that you can calculate from 4 beta strain equal to 4 epsilon tan theta, with epsilon equal to strain. So you can see here, if you want to see that the effect due to crystallite size or strain, so you always go for a small angle peak to identify. You can see your FWHM versus 2 theta, but beta crystallite is following in green path, and this is strain. In higher angle you can see they are coming closer, but in the low angle they are quite far each other. So whenever you go for a crystallite size calculation or a lattice strain calculation, you always try to use that low angle peak to eliminate that overlapping of both those things. So in addition to the Scherrer formula, you can use Williamson-Hall plot, that is B equal to B sample plus strain plus crystallite, that is C epsilon tan theta by K lambda by L cos theta. You can see here, if you plot beta cos theta versus sin theta, you will get a straight line and fitted, and from the slope you will able to get strain epsilon, and from this intercept, that is the K lambda by L, from there you will get the particle size. So you can see here, this is the diffraction pattern of a blue line is bulk area. When you go to a nano, you can see the red line. You can see how much it's broadened. This because of this broadening is mainly due to that this particle size and strain. So those things you can able to identify this using that either Williamson-Hall plot or using Scherrer formula. So there are different contribution of the micro strain on the broadening. So that cause that is like what are the strain effect, mainly dislocation and faulting. You can see this is ideal crystal. All planes are the lines. You can see black lines are aligned properly. But in case of this, you can see there is a deviation of that crystal plane, and here it is a dislocation. This plane is dominated here. So there is no further growth. So this type of dislocation that will cause strain in the system. And if you have a solid solution inhomogeneity, like you are doping some material up to that solution limit, that up to, for example, if you put nickel in zinc oxide, so up to certain extent 5 to 7% it will go inside. So beyond that it will not go into lattice. Instead of going to lattice, it may go to the interstitial or deposit on the surface. So that solution limit, within the solution limit, it has to be, doping has to be carried out. And then there are non-uniform elastic distortion, anti-phase domain boundaries are there. There will be effect of temperature, a different grain relaxation mechanism are there. So those will cause some sort of broadening. If you see the non-uniform lattice distortion, you can see this is a perfectly oriented all these planes, and then here in D0 you can see this is D1 is slightly greater than D0. You can see if no strain is there, this like this, so you will get asymmetric peaks. But when strain is developed, that is elongated in one direction, you can see the uniform strain, the peak shifted, but no shape change. But it's bent like this. You can see on the top and bottom there are different despacing, and what will happen that you will be able to get a diffraction pattern uniform, but it's broadened. So that means a non-uniform strain, if this type of built up, you have many strain effects that come into picture, and finally you will get a quite broad image due to the micro strain effect. So as I discussed the solution limit, you can see this is cerium oxide peak, that's 19 nanometer. You can see this blue peak that is from cerium oxide. This is the red one that you can see 46 nanometer that you have shown the ZrO2 peak. But when you have a solid solution limit, cerium to Zr by doping X from 0 to 1%, you can see here how the peak is like it's broadened and it's going like this. So this is mainly due to the inhomogeneity in the solution. You will be able to get this type of peak broadening. So so far whatever we discussed, that diffraction peak from the position and the intensity, you will be able to identify what is the phase formed, and then from the peak profiling, that FWHM, you will be able to get the this for micro strain or the particle size, the crystallite size that formed. Mostly the X-ray gives crystallite size. So some of the students used to confuse with crystallite size and particle size, because a particle can consist of many crystals. So what you are getting in XRD, it's a crystallite size, but in case of TM, you will see that we'll discuss later. So that there it will be particle size. So the particle may be a polycrystalline material. If it's a single crystal, where XRD and TM will be able to get similar size, but it's a polycrystalline material, so in XRD will mainly get crystallite size, or in case of TM, you will get particle size. Then the third thing that we get from the XRD is from the peak intensity. From the peak intensity, whatever you are getting, so that intensity is mainly coming from three parameters. One is like the whole X-ray. If you see that in X-ray, that is for example, FCC, BCC, or SCP structure in a material or in a crystal, so they are arranged in a proper way. So that means there is a unit cell, and then in the unit cell there are atoms. So in the atoms there are electrons. So when X-ray is scattering from or diffracting from a substance or a material, that means it's scattering from unit cell, scattering from atom, and scattering from electrons. So those scattering from electrons, that is mainly, this is called that polarization factor will come into picture, and from the atom, the atomic scattering factor will come into picture, and finally in a unit cell, the whole total, it will be structure factors. So intensity of diffraction peaks is determined by arrangement of atoms. If your that the FCC, you will get a particular type of diffraction peak, and that intensity will be different. Like the whole IH scale, intensity of that peak will be proportional to the scattering factor square of H scale. That will be the summation of these three: polarization factor, atomic scattering factor, and structure factor. You can see the polarization factor F, that mainly depends upon the atomic number Z value. So that means that A and B, if you combine both, because in the atom electrons are there, so if you combine these two factors, you have a scattering formula, that polarization formula. If you take that using Thomson scattering factor, you can see I equal to this constant terminology into 1 plus cos square 2 theta by 2. So here you can see the F depends on the number of electrons in Z atoms, the angle of scattering sine theta by lambda. That means if you see the XRD pattern, in case of XRD pattern, if you see here at low angle, this 2 theta, if you increase an intensity, at low angle you have intensity peak is quite large, and then this peak will be higher angle peak will be decreased. So this is because you have a scattering factor here. That scattering factor decreases with 2 theta. You can see here, if you take bromine atom, you can see the scattering factor with sine theta by lambda. The scattering factor, how much X-ray is scattering or diffracting, so that is decreasing with 2 theta. Because of that, your peak intensity is decreasing. But in later on, we'll discuss in case of neutron diffraction, these peaks will be, it may be randomly, you will see. At higher angle, you can also observe high intensity peak, because here in neutron diffraction, there is no dependence on electrons. Here it is electron dependence. Here it is, nuclear interaction, that is, it depends upon the scattering length. So that we'll discuss later. So because of the scattering length varies randomly, your peak intensity also varies randomly in case of neutron diffraction, whereas in X-ray diffraction pattern, usually intensity will decrease. So that's mainly because of this, F structure factor dependent on sine theta by lambda. If you see the atomic scattering factor, that means the amplitude of wave scattered by the whole atom by the amplitude of wave scattered by an electron. Like in the atom, you can see the whole atom, there are many electrons are there. So the whole atom, that structure factor, you can define the amplitude of wave scattering from the whole atoms, that is consist of many electrons, and then divided by particular that amplitude y, then n electrons. One electron you consider, and then you divide, you will get the structure factor. So that scattering factor from the atom. But if you see the scattering factor of the unit cell, that FHKL will depend upon summation of F scattering factor of the atom into e to the power 2 pi I H HXN, AYN, and LZN. So these are the structural property, and this will be the electronic property that Fn will get, and these 2 pi depending upon the coordinate X HKL value and XYZ position, will able to get this, summation will get HKL value, FHKL. So that means if the amplitude of the wave scattered by the atom, all atoms in the unit cell divide by 1 electron. So that 1 electron are dividing the whole scattering. So that unit cells consist of atoms and then atoms electron. So summation of all atoms in the unit cell divide by scattering by 1 electron. So if you calculate density, electron density, that will be, you can divide simply 1 by V, that rho XYZ, you will be able to get that electron density, which is a Fourier transform of the structure factor. So you can able to find out that that structure factor depending upon that, whether it's FCC, SCP, what type of structure. If you see a simple cubic structure, you can see only in simple cubic, as you know, all atoms are at 0, 0 position here, at 0, 0, all corners or atoms are there. So because of that, if you calculate that Fj equal to I, this formula, if you apply 2 pi this, and this parameters, you consider all these equations, that what will you find, that F square equal to F square, small f square. That means F is independent of the scattering of HKL plane. So atoms are at the corner, so that this F is independent of scattering plane. So it doesn't depend upon the plane, because there is no atoms on the planes here. So only the corner atoms. So F square equal to F square here in case of simple cubic. But if you take FCC, there are atoms in the all plane, you will find one atoms, and one atom is the back plane. So there are different atoms on the planes. So because of that, the HKL unmixed allowed and HKL mixed allowed. So F equal to 4F of times that. If it's mixed, then F equal to 0. That means 1, 1, 1, 2, 2, 0. This type of plane, your scattering factor will be 4F. In this case, it will be almost 0. And see, depending upon the atom position at 0, 0, 0, half of 0, these are at the half of the plane. If you see the coordinate of this will be half of 0. So considering this an equivalent position, you will be able to find out that. So as I discussed earlier, that NaCl and KCl, we are used to see that in KCl, that isoelectronic, that one plane, that one plane used to mixed. But in NaCl, that peak is there. So those thing what we discussed in presence of isoelectronic, so that we can see in terms of this is scattering factor. You can see FHKL here. In case of it's all even, in case of NaCl, this is 4FNa plus 4FCl, but in odd this is 4FNa minus 4FCl. But in case of KCl, being isoelectronic, you can see the structure factor 4FK minus 4F chlorine, that potassium chlorine atom, they cancel each other, almost zero. So because of that isoelectronic and structure factor being zero, you can see here this 1,1 plane is almost absent here. You are able to see this plane in 1,1,1 here. So that thing can be explained by the structure factor. So then the total intensity of the diffraction being addition to the structure factor, there are other factors that also contribute to the diffraction. That is, one is multiplication factor is there. So scattering factor that we already discussed, and multiplication factor. So number of equivalent scattering planes are there, like 100 plane, there is 6 plane, like 100,001, like this type of cubic system. Different planes are there, -100. So depending upon those planes, so there will be number of equivalent scattering multiplicity coming into picture. Then there is polarization factor, wave polarization will come into picture. Then is the geometric position, because 3 geometric position is possible. So because of their Lorentz factor will come into picture, and some X-ray, maybe some absorption occur by the specimen. So 1/2 mu the absorption factor, or a divide temperature, that e to the power -2m divide. So that temperature defect will come into temperature factor will come into picture. So all these factors all together, define the intensity of the peak. So this equation is like this. So here it is. This is structure factor will come, then there is a polarization factor, and then temperature factor, and then there is a absorption factor here. So this is the structure factor. So all these factors come into picture, you will get a particular intensity. So if you see the mixture of phase, if you see an XRD pattern, like for example, you see glass, in the glass you are getting a broad amorphous peak. In cristobalite, you can see there is a blue fixture peak position. In quartz, there is different type of X-ray diffraction pattern. If all the mix, so those mixed phase, they can be separated out by using X-ray techniques, say X-ray diffraction. You can see even the XRD pattern Al2O3, TiO2, they are mixed. So you can find out what percentage of individual component Al2 is there, how much TiO2 is there. So that can be identified, and how much is amorphous in that material present in the mixture. So those can also be distinguished by using proper calibration. But if you see here, by quantitative phase analysis, that means you can do using extensive X-ray diffraction studies. You can see, you can use a alpha and beta 2 mixture, or the fractions are there. If you do intensity of that I alpha, I beta, a linear curve here, so then this with high quality of data, you can quantify each phase present, and it must make a constant volume absorption, that it should be a linear relationship, and ratio of the peak intensify the I alpha minus I beta is equal to K into X alpha by X beta. So K is a proportionality constant. You can identify the alpha and beta component. If a reference standard, that reference ratio, the K Ri alpha minus Ri beta, from that you compare, and whole you can find out by using that whole pattern fitting, by using Rittville refinement analysis. W, that weight fraction of the particular thing, the Rittville scale factor, and then you consider that ZMV, that mass and volume of the unit cell of alpha, and that of the total. So then you will be able to find out that quantitatively the particular phase is present or not. And then this, you can use this Rittville method that uses the fundamental calculation from crystal structure model to produce a calculated diffraction pattern. Whatever the diffraction pattern you get from the instrumentation, from the X-ray experiment, and then by using this Rittville analysis, theoretically you can calculate that, considering the plane, position, space group, and all these things. So you can calculate that a model, and then you can, using the least square based minimization algorithm, to obtain the best fit between the structural model and the powder diffraction pattern. and starting model is required. You always, when you go for a comparison, the starting model is required. You should know the crystal system, so then only you can use this. And peak position, peak intensities are constrained by the crystal structure model, and crystallite size, microstrain, orientation, all those things that can be refined in the technical model. You will be able to find out that particular, how much accuracy your diffraction pattern is getting. And then quality of the structure refinement and the solution is given by the residual index R factor, that is, this relation F0 minus F observed minus F calculated by F observed. You will get R factor, if it's that will define how your crystal's refinement is good or not. So this is the literal formula. You can see that the scaling factor is here, then multiplicity factor, as I told, the MK is there, then there is a preferred orientation, like there is a thin film, particular direction is oriented, like 100 peak is there, is oriented in one direction or multiple directions, so that you can see the PK value, that preferred orientation, then structure factor will come, then this Lorentz and polarization factors, and then peak profiling, that the width that you are getting, that FWHM, so those pre-profiling can be done, and then the observed value YVI background, so you'll be able to calculate that whole tutorial analysis. So after following this analysis, you can able to find out that structural variables, you can find out atomic position, fractional occupancies, and atomic displacement parameters. All the structural variables can be determined, and profile parameter like peak shapes, including width, asymmetry, some sample height, and transparency, unit cell constant, so those things. And then you have to use the correction terms like absorption, surface toughness, preferred orientation, by using all those things. Like for example, if you take a select suitable crystal, you have to choose, then crystal system unit cell dimension you have to provide, and full data set and collection you have to merge, and using Brevis lattice and space group, and finally you will get the refinement, structure refinement you'll able to get by using the tutorial analysis method. Just one example here is lithium magnesium LiMgBO3 compound. You can see this, the Y observed with the red line and Y calculated the black line. You can see how much errors are there in this, and then you're able to find out all those ABC constant and the volume and all other parameters you can able to find out using tutorial analysis. It's quite difficult to show that complete analysis in this class because of time constraint. I have just given an example. You can do this using the analysis software by guiding full proof or some other technique to able to identify the crystal structure. Means the determination of absolute crystal structure from powder data is quite impossible because of the overlapping of H scale and H minus H minus scale minus L value, and you have limited data. For limited data, constraint, the bond length, bond angle, bond composition, those things also necessary sometimes. The methods work only if you have a good starting model. These are some of the drawbacks that this analysis have. If you don't have a good model, then you will have ended up with something wrong result. So we mainly in today's class, what we discuss? We discuss about X-ray diffraction techniques. So how this X-ray diffraction techniques helps in identification of a unknown material, and from that phase identification, especially composition and abundance, both quantitative and qualitatively, we can find out that the phase composition, and then from the peak profiling, we'll able to find out that crystallite size, microstrain. In addition to this, from crystal structure, we can identify lattice parameters. We can identify as well as if it is a oriented structure, the epitaxial growth or preferred orientation. We'll able to find out the structure analysis that we will discuss in next class when we go for this grazing angle XRD or thin film XRD, and even in high temperature, high pressure study is also possible. Especially if you see the peak position, this is the peak position 2 theta value, that will tell us about translational symmetry, namely what is the size and shape of the unit cell. So that you will get from the peak position. But the peak intensity, this peak intensity, you will able to tell about, you will get information about density inside the unit cell, where the atoms are located. So atoms and positions can find out from there, and then from peak shape as well as width, the FWHM, and how the profiling, you will get the information about a perfect crystal. So basically, that X-ray diffraction techniques is a best technique to identify the phase of whether crystal structure is formed or not within its conventional XRD up to 2 to 3% doping. You can identify. If you go for synchrotron XRD, you will able to even 0.1% doping that you can able to identify. So for whole this study, you can refer these 4 books. That one is solid-state chemistry and its application by A.R. West. So these books are not only for the XRD, this will be for whole part of whole this module of the characterization module, that whatever I will cover in my next all my 6 classes lectures, so that you can refer these books: solid-state chemistry by A.R. West, advanced techniques for material characterization by A.K. Tyagi and Dieter, and elemental X-ray diffraction by P.D. Quality, and material characterization, that is introduction to microscopic and spectroscopic method by Yang Leng. So these 2 books you can even find out online. They are freely available, and these 2 books you can collect from library or somewhere, and you can follow. So all detail about all these techniques. If there is any doubts, either you can mail me or you can ask me here, or later you can mail me.